Okay, ladies and gentlemen, first of all, thank you very much. Okay, welcome all of you to join this ACD guest seminar. Okay, today we are very happy to have Professor Li Jun. And let me give you a short introduction about Professor Li Jun. Okay, so Professor Li's research interests mainly include the development and application of emerging computer vision, artificial intelligence, data analytics, and digital twin technologies for structural health monitoring of civil engineering structures. He has received the Australian Research Council, ARC, okay, Mid-Career Industrial Fellow, and also Future Fellow, okay, very difficult to get. And Discovery Early Career Research Award, and other 3 discovery projects as lead. He is a highly ranked scholar and leads in Stanford top 2% scientists in Korea. He serves as a current member of ARC College of Expertise, Fellow of Engineers Australia, Associate Editor of several leading journals in this area, such as Structural Health Monitoring, Structural Control and Health Monitoring, and International Journal of Structural Stability and Dynamics. He has published more than 250 technical publications, including over 190 journal papers, attracting over 8,180 citations in Google Scholar, with an H index of 53. Professor Li received several research awards, such as Hong Kong PolyU Outstanding Research Postgraduate Young Alumni Award in the year 2024, National Prize in year 2019, etc. His research outcome has been applied to operational condition monitoring of Merthyr Bridge and Stirling Bridge in Australia. The topic today is from sensing to structural intelligence, computer vision, and AI for future smart civil infrastructures. With no further ado, I would like to invite everyone to join me in welcoming Professor Li. Pass time to you.
Oh, thank you. First of all, thank you, Paul, for the introduction. Thank you, Prof, invitation for me to give this presentation. It's really my honor to be here to share with my some recent studies. So good morning, everyone. Thank you for joining this today. And thank you, Paul, for arranging this seminar and the assistant to book the rooms for everything. So today my topics mainly talk about how can we apply computer vision and AI techniques for future smart civil infrastructure, particularly in structure health monitoring and structure engineering areas. I also would like to acknowledge the support from my mentors and collaborators to make those work possible, and the contributions from my former and current team members, and also some larger research grant support to fund this research. Today, I mainly talk about 4 parts, give you a very short background, and then talk about sensing in through computer vision in structural health monitoring, and how can we develop and apply new AI techniques for infrastructure intelligence. Then I give you some brief conclusion. As you may be very aware of this, so urban and remote infrastructure safety is particularly important for society and the community, and with the current challenges such as global climate change, rising traffic volumes, and human activities, and extreme events and natural disasters. Those risks pose a very serious risk to our infrastructure network and the community. So in the recent many years, with the development of new AI, vision, and other technologies, techniques, we have a much more powerful techniques for monitoring infrastructure safety, and those techniques can produce significant cost saving. So that is some accident which have been reported in the last few years on the infrastructures, including bridges and also some larger structures. So this is this is some background in the context of Western Australia. For example, when we talk about climate change, this also impacts the infrastructure in Australia, especially those areas in remote areas. For example, this bridge were built more than 40 years ago in remote Kimberley area, which is one of the fastest area in West Australia, connecting to indigenous communities. So this is the only bridge that can connect to the main areas of Perth in West Australia. But this bridge was collapsed after a flood in 2023. With this is a 1 in 100-year flood. So that is the impact owing to the climate change, because when this bridge designed, they would not expect such accident or frequency or occurrence of extreme events. And for larger bridges, we also expect larger effect, for example, heat wave or growing storm and strong winds or accelerated deterioration from the ocean environmental. So those pose significant challenges for maintaining and protecting the infrastructure safety. So my research theme is on smart, resilient infrastructure. So we make use of vision, smart sensing, robotic system, data, and AI techniques, and or even some IoT sensing techniques for smart monitoring. And we develop digital twin models and make use of edge and the cloud platforms to achieve a smart management system or platform for infrastructure and maintenance and safety evaluation, including looking at the safety, reliability, resilience, or life cycle performance of those infrastructure. So some particular and specific challenges I would like to talk about today is those. So for example, how can we develop and apply those techniques I mentioned, for example, IoT sensing, vision, AI, those techniques for real-world applications in structural health monitoring, and how can we obtain meaningful and high-quality data if we want to reliably use AI methods in particular applications in structural health monitoring, and how can we develop cost and computational effective AI methods for those large scale infrastructure applications, because we know many AI methods, they need a large amount of resources and computational demand. And how can we develop scalable techniques for effective applications to a population of structures? That means we could not only monitor one specific individual structure, but also we can extend to a range of different structures in a region or in an area, but at a reasonable cost. So first, I talk about some computer vision methods. So in the last few years, we have developed computer vision techniques by using static cameras. For example, two static cameras, one static camera, or UAV for measuring structure vibration displacement. This include two-dimensional and three-dimensional displacement measurement, and we can apply AI methods to track the images, to track the key points in the images and match those key points in the video images to obtain accurate and minor structure vibration displacement. So based on those measurements, we can do model identification, condition monitoring, and we have validated our techniques on some real bridges for engineering applications. So this is one example I show here for vibration displacement by using motion magnification technique. Because this example is particular for minor displacement measurement. So from the original video, you could not see any movement, but by using the motion magnification technique, you will be able to see the amplified uh, motion through the video so that we can measure the displacement more accurately. So based on that, we can do the target-free three-dimensional displacement measurement, and we can achieve accuracy level of 0.1 millimeter. But we need to understand it is usually more challenging to measure the vibration displacement in the depth direction from images or videos. That means if we look at the vibration displacement in the depth direction, for example, the later displacement of this bridge, that will be more challenge. That is because the depth information need to be retrieved from these video images. And based on that, we also do some studies by using UAV. So you can see this is a testing we set up. We use two cameras and a UAV. We try to compare their responses obtained from those video images for this testing structure. We also set up some laser displacement sensors for providing the baseline information, and we can demonstrate even from the UAV videos, we can get the accurate vibration displacement measurement. And you can see the scale of this displacement is also very small. It's from 0.5 millimeter to about 2 millimeter. So that is very small scale, minor vibration displacement measurement, giving the effect of movement or vibration of the UAV itself. So that is some part we need to eliminate the effect from those UAV motions. And this left side is an example. We use a camera, is a consumable camera. This is which is a GoPro, because this test was done in COVID. So the student only did the test in the lab by using the very limited experimental resources. So the key repeatedly put this GoPro camera at different locations to measure only one segment of this bridge under the moving load traffic. And by combining those different test video images, he can achieve the model identification accurately. So he can identify the natural frequency and the mode shapes accurately by combining the mode shape information and the natural frequency information obtained from different segments. So that is one trial. We try to use only one camera for the model identification of relative large scale structures. Later this year, we further developed a deep learning based motion magnification for minor displacement measurement. So that means now we use AI techniques to define and improve the parameter settings and improve the performance of motion magnification. So traditionally, the motion magnification techniques need to have a specific frequency to amplify. So that means you need to define the frequency range of the structures in the video. You need to amplify. But with these AI techniques, we don't need to do that. And we can also improve the blurry and the distortion effect in the video images. So that means with less input to the AI model, and we don't need prior knowledge on the frequency range. You need to know for the motion magnification. And these techniques can also improve the motion magnification results when dealing with blurring and distortion effects in the video images. So that is the idea of these measures. And we also did some tests in the lab. So as you can see, this is a cantilever beam set up in the lab, and we used some accelerometers and laser displacement sensors to provide the baseline information of the structure, so we can have the ground truth displacement measurement for this beam when it is vibrating, and also we can measure the accelerations on the structure for identifying the natural frequency and mode shape if you want. And we use the camera to record the video when the structure is vibrating. And based on this vibration video and the developed deep learning-based motion magnification techniques, we can have the very accurate displacement measurement even for the scale of 0.1 millimeter responses and 0.01 millimeter displacement. So if you zoom in that responses, you will see quite accurate displacement can be obtained in those cases. So that demonstrates the improvement of this AI enabled motion magnification technique accuracy. And for the model identification, very accurate natural frequency and mode shapes can be obtained from displacement measurement. So that is another study. We simulate a vehicle traveling on a bridge. So we use the camera to record the vibration video of this structure when it is subject to this vehicle loading. And we simulate different lighting conditions. For example, normal lighting conditions, you will see some structure figures on the image. For example, these are some bolts in this area on this structure. You will see that relatively clearly. And we simulate the dark and the very dark conditions. So from dark conditions, it becomes more difficult to see very clear figures and the bolts on these structures. But with our developed techniques, we can still quite accurately measure the displacement even at the scale of 0.1 millimeter. So that demonstrates the accuracy and the improvement of those techniques under very dark lighting conditions. So this is some study we demonstrate how can we use this vision-based technique for condition monitoring. So this is also the same structure we used in the last test. This is a vehicle loading, and that is a bridge. We simulate different damages by losing some bolts in this bridge model, and we did that moving load test. We record the videos, and then based on this, we define some damage indicator to indicate the condition change in the different girders. So observing those static outliers and damage indicators, we can identify the condition change in the structures based on this vision measurement. So that tell us the information about the structure condition from the vision supported sensing technique. Also, we did some studies on real highway bridges in Perth. So this is a continuous bridge in Fremantle. We set up camera and some fixed sensors, traffic cameras on the bridge to monitor the traffic flow on the bridge. And we use these cameras to look at the specific area of the bridge to obtain the vibration displacement of this bridge. So we use some figures on the bridge itself to serve as a key points, and we track the movement of those key points in different frames of this video, so that we can get the vibration displacement in continuously during the video from the camera. So those are some typical results we get under different traffic loading conditions. So we can observe that there is a significantly large displacement, for example, 8 mm, when that is relatively high traffic loading across the bridge, and also for some larger traffic loading scenarios as well. So we can use this to test the allowance of the bridge deflection under certain heavy loading conditions. This will provide some information to the bridge management authorities to understand the deflection, maximum deflection they can observe under different loading conditions, especially those heavy traffic loading scenarios. And they can check that with the design guidelines to see whether that's still in the limit of the loading bridge deflection allowance. So next, I talk about some recent work on developing edge intelligence and vision techniques for structural health monitoring. So one significant change or further development of these techniques is we integrate the vision techniques with the edge computing capacities, so that we can provide on-site computing capacity and on-site sensing capacity to immediately reflect the conditions of those structures and transfer the key information to the cloud for the management. So that is the design flow or methodology flow of this. So we use this edge device. This is installed on the bridge. So that is pretty much an NVIDIA edge node, and we connect the cameras to this edge device by using this camera to look at the specific areas of the bridge, so we can monitor their displacement, their conditions, and by getting their displacement, their vibration information, we can have those dynamic information and also larger key information. You can transfer this key information to the cloud. So we use Amazon Web Service to build a digital twin model on the cloud. So you can access the data from anywhere on the internet. For example, in your office, to look at the bridge information connected from this device. So you will see the vibration responses and some further analysis results if you want. And also you can look at the conditions of this device itself. So those can be used to generate any report if required to the users. So that is the hardware we used for this idea. So this is NVIDIA edge device. Originally, we use Jetson Nano. Now you have much better hardware. So we also upgrade this as well. And we can connect cameras to this edge device, so like this. And this is a power supply. Of course, you can use a portable power supply, or you can use larger power resources. This can be used to supply the power to the camera and to the edge device. And we use 4G modular to transmit the data to the cloud, so that we can have immediate feedback of the structural responses or conditions, and those are accessible from the internet. So that are some specifications of this hardware, and also the cost is totally less than 1,000 Australian dollars. So this provide a relative affordable and cost-effective system to measure the responses of the structures, provide the data, and connect the device to the internet, to the cloud, so, and also provide a dashboard for users or owners to manage their system. So this, for example, this is a visualized structure in this dashboard. So we used a tower as an example. Of course, you can use another structures, for example, a bridge. Then we can see the displacement responses at different locations of the structure by using the cameras looking at the different locations or using multiple cameras if you want. And then we can also look at device temperature and video processing frame rate or CPU and the GPU usage that tell us the information about the device itself. And then if you want to further develop, you can develop some signal or data analysis processing modules on this to process those measured data. So this is a validation in the lab. So that is a tower structure I just showed in the dashboard. And we installed some cameras and some laser displacement to serve as the baseline information. And those is our device. So we try to look at some those locations and to validate whether we can get the very accurate displacement comparing with those laser displacement sensors. So that tells us the accuracy of our and the performance of our device and the method. So this is some preliminary studies by using different frame rate, different track methods for the key points. So that will tell us how to best select the ROI methods. For example, how big a, a region of interest you will need to choose and what methods you are going to use to select or identify those key points in the videos. So based on this study, we have a relative optimal ROI size, and we use that size and specifications for obtaining the displacement. So that is the results we obtained from this device and also from the laser displacement sensors. So the blue is the ground truth connected from the physical laser displacement sensors, and the red one is our device results. So you can see the proposed device and approach can give you a very accurate displacement measurement results, and from the root mean square errors and correlation coefficients. So you can see a very good correlation can be obtained by these methods. So that tells the effectiveness of these methods for measuring the displacement. So further on, we try to demonstrate how can we apply this to monitoring of real bridges and how effective that will be. So we developed a multiple edge camera system. That is, this is a 6 camera system, all connected to one edge device. So that means we use one device to support 6 cameras, but these 6 cameras will look at the different regions of this bridge because this is a relative long, cable stayed bridge, and we look at different areas of this bridge by using the cameras. So we can measure their displacement, and we use those measurement information to identify the natural frequency and the mode shapes of those structures. And so that is our results. So you can see based on the ground truth, based on our approach, we can identify quite accurate results and the consistent results comparing with the traditional accelerometer-based results. So that demonstrates the feasibility of using these methods and the device for real bridge monitoring. So next, I will talk about some AI techniques for structured health modeling, particularly on using and developing generative AI techniques for crack detection, and also some larger applications or development in structural damage identification or data processing and so on. So that is something I would like to talk a little bit more on this part in AI applications. So the idea is pretty straightforward. We use large language model to generate the effective and accurate promotes, and we use diffusion models to generate crack images that solve the problem of for some real structural health monitoring crack detection areas. We don't have a sufficient number of high quality images of cracks on different types of structures. So by using these generative AI techniques, we can significantly enlarge the training data and the data size you can have. And also we can improve the diversity and the balance of the data set you will have. And this will improve the crack detection performance. And based on this, we can do the further crack segmentation. So that is some generated images based on this approach. So that is some promotes we generated from large language models, and this is the objective detection results. So we can generally have a better detection. So this is only for the object detection. So that means we identify the cracks and locate their areas by using a box. Then we detect those crack objects in the images. And of course, if you want to further identify the crack width and length, that means we do the crack quantification. We also do that based on the point clouds and AI methods. So that is another study we conducted by using multiple view images to build a digital model and based on point clouds. And based on that model, we can do the segmentations of the cracks, and we can identify the crack widths and the lengths along the cracks. So that is a very detailed crack identification results. So for example, for a beam structure in the lab with many different cracks, so based on this point cloud model and AI methods, we can not only detect the crack, but also we can segment the cracks and provide the width of the crack and the total length of the crack. So that is some results on the crack detection and quantification. So that is some. These are some our previous studies. I probably go through this quickly because this has been published a few years ago. We have applied AI techniques for lost data recovery in wireless transmission. We can recover the lost data in the transmission process, and we can use these AI techniques to do response reconstruction, signal denoising, structural damage identification, so we can identify the damage pattern and the damages in this area. So the next and the last probably topic I want to talk is the drive-by methods. I probably use another 5 minutes and leave some time for the discussions. So this is a IoT sensing methods, and we develop these along with the drive-by techniques. So the idea is we install the IoT sensor on vehicles, and we use these vehicles to cross a large number of infrastructure, for example, bridges and roads in the city, in the area. So we connect the IoT sensor information, including their vibrations, and also the GPS and other informations, and even cameras if you want. And then we transmit this data to cloud and to further processing. And we try to make use of this information to monitor the regional level infrastructure conditions, including bridges and the roads. So that is some development on our IoT sensor. So that is a prototype of this IoT sensor. So it's based on Raspberry Pi platform, and we use a 4G modular to transmit data to the cloud, similar as our edge device. And that is a vehicle we developed in the lab. So we install the sensor on the lab, and we use this vehicle to cross over the bridge so we can identify the natural frequency and the mode shape of the bridge. And further on, we install some smartphones on vehicles, and we can actually use the accelerometers in the phone, built in the phone, to obtain the vibration solution responses of the vehicle when the vehicles are traveling on roads or bridges. And based on that, we can do the load roughness evaluation, and we compare with the ground truth data. So those ground truth data are provided by the Manos, Western Australia. They do the survey of those load conditions by using commercial surveying vehicles, and we can have a consistent results in this load roughness evaluation. And further on, we try to develop those techniques for bridge monitoring. So we developed AI methods based on knowledge distillation, and we can identify the useful information from drive-by measurements. So we set up a database. We conducted a large number of repeat tests by simulating different damage scenarios and the different vehicle loadings on this bridge. And we connect a large size of data, and including accelerometers, laser displacement sensors, strain gauge responses, and the cameras. So this provide a test bed for our studies. We can have a large number of training data set for drive-by sensing when the bridge is subject to vehicle loadings, and we have the responses from the bridge. We have the video camera to record the video and have the images. So we can do this test to verify whether we can use AI techniques to interpret the data we connected from this test bridge. So that is the responses, the figures we identified from the last layer of the student CAN model. So that tell us the figures is very close to the contact point responses between the vehicle and the bridge model. So that is the most fundamental important figures we need to use for the further condition monitoring or structural analysis. This result, this observation is also consistent with the analytical solutions of the bridge vehicle interaction problem. So in Professor Y.B. Young's paper, he also analyzed the contact point responses is one of the most important figures that can be used for structure monitoring of the bridges. So that is a quick summary of my recent work and some recent development. So I don't want to repeat the conclusions, but I really hope we can have more applications and validations on real problems of real world engineering structures, And I hope our techniques can not only apply to individual structures, but also to regional scale monitoring in a city or in a large community. Thank you. Thank you for your attention.